Today, we're going to spend some time talking about what mechanical engineers do with math and calculation software. Specifically, we'll discuss the tools and features in Maple for mechanical engineers, and we'll walk through some applications as well. And it's the latter point that I get really excited about, real-world analysis using supporting tools like Maple. If you go to the Maple Application Center, you'll find thousands of application worksheets across many domains, including many for mechanical engineering. And we're going to demonstrate some of these applications in a few minutes. There's lots there, lots for you to play with, and I do encourage you to spend some time browsing the material that's available. First of all, before we dive into Maple proper, the bigger picture. Many of you may already be familiar with Maple, but some of you may not have even dipped your toes in yet. Maple's a tool for mathematical computing with a notebook-like interface that lets you document as you calculate. There's a big library of mathematical functions. There's also a programming language with support for units and dimensions and many different data import filters. There's also interesting tools like built-in thermodynamic and transport properties for fluids and scientific constants as well. The Maple interface is the reason why a significant number of mechanical engineers use Maple. It's pretty unique. A Maple document itself is a rich environment for math and documentation. You can include equations in natural mathematical notation, explanatory, fully formatted text, just like a word processing tool like Microsoft Word, hyperlinks, tables, images, animations, and lots of other stuff. This means you capture the assumptions and background information behind an analysis, as well as the actual number crunching, the calculations. I'd also like to highlight the quality of Maple's plots. You can produce some really visually impressive plots and charts, and we've provided you with many ways to finesse and fine-tune the look and feel of those plots, right down to the precise color grading of the color range on a plot or a spectrogram. The plots and visualizations are inline in a worksheet. That gives you a far closer connection between your analysis, the algorithm, the equations, and its visual representation. Now, at this point, what I'd like to do is dive into Maple and show you a few applications. Now, everything I show you today is available on the Application Center. But I'd like to walk through maybe 3 or 4 mechanical engineering applications. Let's start off with the basics, the static analysis of frames and trusses. Now, the theory of static analysis involves concepts such as the condition of static equilibrium, the method of joints, the method of sections, and so on. Applying this theory to maybe a system like this, a 4-member frame, leads to equations that describe the forces and moments in a system. These equations have to be methodically derived and dimensionally balanced. Having said that, let's look at this worksheet. So at the top we have a title, description, and a diagram of the problem. This diagram was simply copied and pasted in from another application. It's a 4-member frame, and we're going to analyze the forces in the system. Below this, I have some parameters I've defined. So loads and load angles and lengths. All of these have units associated with them. So loads are in newtons, angles in degrees, lengths are in meters, although these dimensions could be in any consistent set of units. And below that, I have the equations that I've derived. Let's take this step by step. First of all, I calculate the sum of moments about A, that's this point in this frame system. Looking at this equation in particular, I have things like little subscripts and easy to read Greek letters. It's a nice crisp equation to look at. I then solve this equation for a force, and Maple returns the result in newtons. Now I can rescale this result to any dimensionally consistent unit, such as kilonewtons or even pounds force. So all I have to do is expand the context panel on the right-hand side and enter my desired unit into this box, say pounds force. If I hit enter now, that force is rescaled to pounds force. Now, as I progress through this document, you can see that the equations are crisp and readable. I have text sprinkled about various places and more images. Now, once I've finished my analysis and assembled my document, I can print it out either to paper or to PDF. And this is what it would look like in its printed form. It's well presented, it's formatted, it's readable. So the documents that you develop are readable, they're shareable, you can audit them easily, check for errors, and frankly, they're just better than hand calculations on paper or even spreadsheet analysis. Let's move on to something else. Let's talk about kinematics and dynamics. So we're looking at this quick return mechanism, this slider crank. You can enter kinematic equations and geometric relationships, including different differential equations, again in auditable natural mathematical notation. In this worksheet, we'll break down the motion of this slider crank. First of all, the displacement analysis. Let's say I want to plot the displacement S and the angle beta as a function of the angle theta. All of the other parameters are known. Now look at these two geometric relationships for S and beta. Using Maple's solve command, I can manipulate and rearrange these two equations to give explicit expressions for S and beta. This command did all the heavy lifting, the solve command. It's one of Maple's many math functions. If you right-click on this function, you can jump straight to its help page here. And I want to highlight the quality of Maple's electronic help. It's something that we've worked hard on making easy to use and easy to understand. At the top of each help page, there's usually an explanation of the syntax. Nearer the bottom, there's worked examples that you can simply drag, copy and paste into your own worksheets. There are usually links to more details at the very bottom, and on the top right-hand side, there's a bunch of other links floating about, and these are links to relevant, related help pages. And these are a great way of learning about the wider ecosystem of Maple. Now, once I've derived my explicit expressions for the angle beta and the displacement S, I can generate a visualization, a plot. So here, I have a dual axis plot. So the angle beta in blue and the displacement S in red. Once I've generated a plot like this, if I right-click on it, I can change aspects of its visual appearance, or I can export it to an external file. I like exporting things to SVG format. It's a vector-based graphic format, so the exported plot looks sharp and crisp even if you zoom in. Onto the velocity analysis of the system. I think this is probably the most interesting part of the velocity analysis. Here I'm differentiating those two geometric relationships that I defined earlier with respect to time. So you end up with a bunch of differential equations that, again, you can get Maple to solve numerically this time. And of course, you can plot the result. And to end this worksheet, you have an acceleration analysis based upon differentiating the velocity equations. Let's move on to the next application area, and my own personal interest falls in this field, thermodynamics and thermal engineering. You can use Maple to calculate the heat flows around thermodynamic cycles, such as a Rankine cycle, Brayton cycle, and other thermal cycles. You could even optimize the system to maximize parameters like the coefficient of performance, or to drive the system to a specific set point. These applications use Maple's database of fully computable thermodynamic and transport properties for fluids, and this data is units aware. So here, in this application, I'm examining this vapor compression refrigeration cycle. The working fluid is the refrigerant R134A. Let's start off with the compressor. Assuming I know the state of the fluid entering and exiting the compressor, I can calculate the work done by the compressor. So that involves extracting the enthalpy of the refrigerant as it enters and exits the compressor. When the refrigerant enters the compressor, I know it's a saturated vapor at 253 Kelvin. I can give those states to this command property from the thermophysical data package and ask it to give me the enthalpy. And here it returns the enthalpy, again with units attached to it. Again, if I wanted to, I could rescale this unit to any other system, such as BTU per pound, or something even more esoteric, such as BTU per ounce. All I need to do is enter the dimensionally consistent unit I want to see the result in. I also calculate the enthalpy of the refrigerant as it leaves the compressor, and the work done by the compressor is simply H1 minus H2, the enthalpy of the refrigerant entering the compressor minus the enthalpy of the refrigerant leaving the compressor. One thing I want to point out is that I've used temperature and quality and temperature and pressure as states when I'm calculating enthalpy. You can use many different independent quantities as states, such as temperature and entropy and quality, and so on. Now, progressing through the other unit operations, in the same fashion, I calculate the enthalpy in and out of the system. So the throttle, the evaporator, and then I can calculate the coefficient of performance of this refrigeration cycle by dividing the heat extracted by the evaporator by the work done by the compressor. And here the coefficient of performance is 2.2. The higher the better. And to cap this off, I can plot the flow of energy across the refrigeration cycle on a pressure, enthalpy, temperature chart. Again, this is one of the built-in plots in the thermophysical data package. Now here I'm using the refrigerant R134A, but that has a pretty high global warming potential. So the 100-year global warming potential of the refrigerant R134A is about 1,430. That's pretty high. It's actually being phased out because it's a pollutant. There are many other refrigerants being explored as alternatives. I think a popular alternative is the refrigerant R1234YF. I think that's it. If I simply want to see how this refrigeration cycle operates with this refrigerant, R1234YF, all I have to do is replace this refrigerant here and execute the entire worksheet. So if I click on this button, those changes cascade down the length of the Maple worksheet, and all of the plots, charts, dependencies, results, updates. So here you can see the coefficient of performance has dropped, and the refrigeration cycle has been updated on this PhD chart. Continuing on the same theme, you can actually create interactive applications like this. Now, this is a model of an organic Rankine cycle, and these are often used to recover low-grade heat, for example, from factory exhausts. In this type of application, I don't see any math, any equations at all. All I have are a flow chart, a summary of results, and a dashboard which allows me to change various parameters. So there are drop-down boxes, text boxes which allow me to change parameter values, and I do this. You might see some of the numbers in this flowchart changing. This plot updates as well. This type of application I can actually deploy free of charge using the Maple Player. That's a free runtime engine for interactive Maple applications. It's a free download. I think if you Google the Maple Player, it'll be a first link. It'll be the first link. So we have many mechanical engineers who use the Maple Player to deploy their analysis. I've already shown you one typical application, and here's another application. It's a gas orifice flow meter calculator. Again, I have text boxes, drop-down menus, buttons to update results. As well as those UI elements, I could have also used sliders, dials, gauges, widgets, radio buttons, checkboxes, and so on. Let's finish with this. This is kind of fun. Another really popular application of Maple for mechanical engineers is robotics, and mechanical engineers are at the forefront of designing robotic systems, from both the geometric and mechanical design to writing the controls and system software. This application models the motion of the tip of a 3-degree of freedom robot, and I'm just going to drop straight down to the very bottom and show you the result of the analysis. This is just a robot's arm, and the tip is just writing out MapleSoft in handwritten cursive writing. This looks neat. Now, I won't go through this entire worksheet in excruciating detail. I'm just going to highlight some important features from this worksheet. At the top, I derive the transformation matrices for the system. So these matrices are typeset-like matrices. They contain symbolic properties. Moving on, the worksheet then computes the equations that describes the angle of each of the joints using Maple's solve function. Let me just rerun the entire worksheet. So the equation for the first angle is pretty simple. But the equations for the second and third angle get to be pretty big. This isn't something that I'd like to do by hand. One cool feature I do want to highlight is code translation, and it's a really common use case for Maple. We have many people who use Maple to derive large symbolic equations, and then they translate the syntax of those equations to another language, such as C or Python. Let me show you what that looks like. So here I'm using Maple's code generation package to convert the equation that describes the third angle to C code. I could also convert it to Perl, Python, Java, Visual Basic, and a variety of other language targets as well.